Hello and welcome to our webinar, The World of Static Analysis, with my colleague, Mr. Roy Lütke. Short introduction of ourselves and our company. So the main person in the webinar will be Mr. Roy Lütke, who is the Director of Static Code Analysis Tools at Verifysoft Technology, and myself, I am responsible for international sales at Verifysoft. I will just do a short introduction, who we are and what we offer. The company was founded 2003 in Offenburg in Germany. Our own tools are Testwell CTC++ code coverage analyzer and Testwell CMT++ code complexity measurement tool. We are also distributor for some other tools, for example, Imagix4D, CodeSecure, CodeSentry, Codee. Later on a little bit more about these tools, and we offer also some seminars. We have more than 750 satisfied customers around the world in over 40 countries on all continents. And as you can see, most of them are from safety critical areas like automotive, automation, aerospace, medical, but we also have some other customers, smaller ones and just from other sectors. So this is about our tools which we offer. Our main tool is Testwell CTC++ code coverage analyzer, which is a tool to measure code coverage. It does it till MCDC coverage, which is very important for safety critical areas. It is compliant to safety standards. Is working with all compilers, all embedded targets, and have some interesting features like, for example, justifications. Missing coverage can be justified. It is easily integratable into your CI/CD pipeline and has configurable reports, as you can see on an example. Furthermore, we are distributor of other tools. They don't belong to us, but we are distributor mostly in Germany. It is CodeSonar, which is advanced static code analysis, CodeSentry, which is software composition analysis. It is Imagix4D, which is analyzing, for example, legacy code, and Codee, which is performance optimization tool.
Yeah, thanks, Polina, for the nice introduction. Welcome to the webinar, The World of Static Analysis. Today, I would like to show you various possible applications of static analysis, of course, without claiming to be exhaustive. So this is the agenda for today's presentation. So due to time constraints, I don't want to go too much into detail, but we will rather jump straight into the topic. For those of you who have not yet dealt with the topic of static analysis is also used in soccer. So the coach first considers sequence scenarios and strategies, as well as possible mistakes in the lineup. This is nothing other than static analysis. The dynamic analysis then takes place at runtime, for instance, during training or the actual game. Software development is very similar. Static analysis means taking a look at the source code without executing the application. Dynamic analysis, on the other hand, means running the program and evaluating the runtime behavior. But of course, this then requires test cases. Manual static analysis has existed as long as software development has existed. So it is clear that a developer who writes a program has an idea how the program will behave at runtime. So on this basis, he or she can eliminate errors during the writing process. It was proven to be a good idea to have a second developer by your side to carry out a walkthrough together as part of the review, as it is easy to overlook your own errors. So in recent times, static analysis tools that can perform checks automatically have become increasingly powerful, and far surpass manual analysis in terms of depth and reliability. So what are the strengths of automated static analysis? These tools are very strong in detecting undefined behavior. For instance, by the use of syntactic analysis. So a compiler also has the ability to do this, but analysis tools usually function in greater depth. They carry out semantic analysis, that is, check the meaningfulness of the syntactically correct code. So be aware, you can also program syntactically correct nonsense. So I'm a really specialist in this. So in my life I have implemented a lot of nonsense. So these automated static analysis tools can carry out data flow analysis, means to uncover uninitialized variables. They perform control flow analysis to find inaccessible code, also known as dead code. And very importantly, the paradise discipline of static analysis, concurrency analysis. Therefore, I would like to expand on this area of application. So here you can see pseudocode for two typical concurrency problems. On the left side, you see a race condition, more precisely a data race. The two threads created here, two POSIX threads, which run both through a common function that increments a global variable, sum. Now, this expression here is not atomic. It is processed in several steps internally, and if both threads run through this expression at the same time, they will write to the same addresses. And of course, this inevitably leads to conflicts. How can this be avoided? Clearly, blocking such critical sections with mutexes in the solution. That way, only one thread at a time can run through such a section. On the right-hand side, I have synchronized the critical sections, albeit not very intelligently. Now I have two functions here. The first function is run by thread A, while the second one is run by thread B. In each function, we also have critical section. We also have a critical section, but this time synchronized with mutexes. So the following situation may occur. The first thread fetches the first mutex, mutex 0 here. Meanwhile, the second thread fetches the second mutex, mutex 1 here. This blocks the first thread, since mutex 1 is already held by the second thread. And the second thread is no better off as mutex 0 is held by the first thread. So this means that both threads are blocked and are waiting for a release that cannot take place. They are waiting for all eternity, and if they have not died, they are still waiting today. These are two typical concurrency problems. Critically, they do not necessarily have to appear in dynamic testing. They are non-deterministic. We may not see any errors during the test runs, and the deadlock may not occur there either. According to Murphy's law, this will certainly happen in productive operation. However, static analysis can reliably detect such problems and therefore is indispensable for checking applications that have implemented concurrency. Check for compliance with coding guidelines. So another task that static analysis tools can perform is checking for compliance with coding guidelines. There are both proprietary and standardized rule sets like the MISRA rules. So I've listed a few rule sets here as examples for which if added here to help ensure a certain software stability and quality. Here, for example, we have the AutoSAR C++ rule set. This is 60% identical to the MISRA C++ rule set. So therefore, it has been decided that the AutoSAR C++ rule set will soon be merged into the MISRA C++ rule set. So I've listed other rule sets here, from Lockheed Martin to the National Astronautic Space Agency, while the last ones focused more on security. So the blue ones here, listed here. So these are focused more on security, that is security against external attacks. So another topic is checking for maintainability. So I'm targeting metrics here. So there are more than over 100 known metrics. So the simplest metric is the number of lines of code. So I have too many lines. If I have too many lines of code per function, it is very difficult to understand the control flow and the logic in a reasonable amount of time. So this increases maintenance costs and the risk of making mistakes when changing the code. Another metric is, for example, cyclomatic complexity according to Watson and McCabe. So this is based on the complexity of the control flow. If the code of a function approaches the dreaded spaghetti code, it becomes incomprehensible and maintenance costs increase. Other example would be Halstead's implementation estimates, which are also well known. HIS and KGAS are conglomerates of well-known metrics compiled by various car manufacturers. So what is the area of application? So, production critical applications with high functional safety requirements. So, but what are critical applications? Applications that could endanger human life or cause major economic damage if they do not function properly. However, so if there is a, for instance, a coffee machine that does not work properly, that can still drive the manufacturer to ruin. Under the bottom line, so wherever you want to make sure that the software works properly. Security analysis. So security is a topic that is becoming increasingly important. That is protection against external attacks. Static analysis can also help here. In the past, we were only familiar with DevOps, or so-called development operations. Security analysis was always somewhat neglected in the lifecycle, and extra team had to take care of it. However, we quickly learned that this drove up costs. If a security vulnerability is discovered, this inevitably leads to a change in the source code, which then needs to be retested. If this becomes necessary at an unfavorable stage in the lifecycle, additional costs naturally arise. This is why static application security testing is introduced at the start of the implementation phase. And this is known as DevSecOps. So when we talk about security vulnerabilities, what are we talking about? A few important ones are mentioned here. So buffer overrun and underrun, as well as format string problems, allow attackers to inject malicious code into affected applications. Or hard-coded passwords can remain in the source code due to carelessness during testing. The use of system is disguised in the source code. This is often an attack from inside. So dissatisfied employees often install a backdoor that way. For further execution, we need to define two terms beforehand: zero-day vulnerability and N-Day vulnerability. A zero-day vulnerability is when a security problem has just been discovered and was not previously documented and published. Zero-day vulnerabilities are relatively harmless as potential attackers are not yet aware of them. N-Day vulnerabilities, on the other hand, are much more dangerous. So these are problems that have already been documented and published. They should immediately be eliminated in applications. So here I have tried to explain how different static analysis techniques can be applied. So a typical application can consist of self-developed, open source, and purchased commercial third-party components. The self-developed part is of course available as source code, and the errors and security vulnerabilities contained are homemade. A zero-day source code analysis is recommended here. The same applies to the integrated open source components, as the source code is usually also accessible. With regard to open source components, it is also advisable to check for known security problems by researching the relevant vulnerability databases. So if the open source component is only available as an already built binary file, the static zero-day analysis can also be carried out on the basis of the binary code. Commercial components are usually only available as binary files. So a static zero-day binary code analysis is recommended here in the first approach. However, the N-Day search, which is certainly necessary, can only be carried out once any open source component contained in the binary file have been identified. And this is done by the software composition analysis, SCA. I will come back to this technology later. Finally, once the complete application has been built, a security attribute analysis should be carried out. I will also come back to this later. So, as Polina has already mentioned, so we are providing as a distributor the tool CodeSecure CodeSonar, a static analysis tool that addresses most of what I've mentioned so far. So it's able to perform bug hunting, capturing and calculating of metrics, checks for compliance to coding guidelines and standards such as MISRA, and data tracking. So this is some kind of penetration tests, virtual penetration tests, and it's able to provide security analysis. Software composition analysis. So here I examine binary files for the open source components they contain. In most cases, the open source components contained in binary files are only known to a limited extent. So you have to imagine that an open source component has integrated another open source component, which in turn has dependencies on other open source components. So this can go very deep. It is similar to an iceberg. So the largest part is hidden under the surface. And if the last component in the chain has security problems, so they will be in your application. So that's why identifying them is eminently important. So how does software composition analysis work? The binary file to be examined is sent through a scanner, which first searches superficially for any strings or symbols it contains. So these results are then compared with those in a database for various known components. If this does not lead to a result, it is necessary to go into more depth. An attempt is then made to delimit functions in order to create a call graph. Based on this pattern, signatures can be created, which in turn can be compared with those in the database. As a result, a list of the identified component is created, called SBOM, Software Bill of Materials. Equipped with the knowledge of the binary's open source components, the tool can then access public vulnerability databases and identify any applicable N-Day security vulnerabilities. The check for software hardening, also known as security attributes, has actually nothing to do with the implementation. Rather, it concerns the way the finished software was built, that is the compiler settings. So there are compiler settings that increase the difficulty for hackers to break into the program. As an example, you can see a stack frame of a function here. The typical attack is carried out in such a way that the area of the data to be read is overwritten with executable malicious code, for instance, by exploiting a buffer overrun. So ideally, the return address of the function is also overwritten so that it points to the start of the injected code. This is then executed. How can we prevent this? So there are various options. One software attribute, for example, is a stack guard. So a stack guard is something like a minefield that is created in the stack. That means all addresses in the stack frame that do not contain any data are assigned arbitrary values, and these are checked at runtime. If the area is overwritten by an attempted attack, the application exceeds immediately. So this is one of many ways to protect an application against attacks. So there are many others. So I have listed an excerpt here. But so these attributes can be checked for their presence in the binary by a static analysis tool, and thus statement can be made about the scope of the protection. So what are the areas of application? Of course, we have application development, such as database applications, for instance, ERP systems, trading platforms, and product development, as well as vehicles, machines, consumer electronics, and even for the use of standard software. So it must be ensured that sensitive data cannot be extracted. It is also important for license management to ensure that all software components are operated with a valid license. And of course, a license manager does not want to see an important software program shut down due to an injunction. So, but this is something a static analysis tool is able to inform with. If all the components have been identified, then we also have knowledge about licensing. So we are providing a tool called CodeSentry, which is addressing all the requirements I've mentioned before. So it performs a software composition analysis. It established a software bill of materials after it has identified the components. It uncovers N-Day and 0-day vulnerabilities. It's able to check the binary for security attributes, and it gives you the referring licensing information. It's also possible to use static analysis tools in order to increase the performance. So many people are not aware that static analysis can also be used to optimize performance. So where are the possible approaches for improvements here? So I have listed a few examples here, but due to time constraints, I would only like to go into one example in greater detail. So again, I have here an example as pseudocode. I have created a slightly large matrix here and would like to increment each element of this matrix using an algorithm. On the left-hand side, I proceed column by column, and on the right-hand side, row by row. The right-hand side, that is the row by row access, runs significantly faster. So the reason for this is cache related. So first I need to explain what a cache is. A cache is a memory that is very fast. So why is it very fast? At first, because it's very small. So the smaller the memory, the faster the access. At second, because it's designed as a static RAM, and a static RAM is up to 100 times faster than a dynamic RAM. And at third, because the cache memory is normally installed directly on the CPU's chip. This means that the CPU can load the data directly into the registers without having to take the detour via the bus. For these reasons, so the cache is ultra fast. How does the data get from the main memory in the cache? So this is done by the prefetcher. The prefetcher is a firmware on the CPU that examines the address stream, and based on this, it assumes which data is likely to be needed next. So this data is then loaded from the main memory into the cache. The cache is organized differently from the main memory. So cache lines are not individual cache lines, not individual bytes or data words are addressed in the cache. So I've shown this on this slide. So these are cache lines, or should be cache lines. On Intel systems, a cache line usually consists of 64 bytes. A cache line also has a header. This consists of an address tag as a reference to the associated memory area in the main memory. And it contains a status tag. And this status tag, also known as dirty flag, indicates whether the data in the cache line has been changed. So the cache line is a copy of the data in the main memory. And if the program overwrites data in the cache line must be written back to main memory so that the changes are also implemented in the main memory. If the cache line was only read or not accessed at all, the status tag does not change, and the cache line can then be deleted from the cache without write back if required. So, but why is row-by-row access to the matrix faster? This is quite simply because the data is stored row by row in the main memory. The data in the cache lines are therefore also row-oriented, like the copies. So if the CPU loads the content of a cache line into its registers, it contains all the data required for processing. On the left-hand side, the cache line contains only one usable datum in the worst case. So as the cache memory is very small and can only hold a limited number of cache lines, there is a high probability that the CPU will not have the required data available in the cache. So this data must then be loaded from the main memory in a time-consuming process. I think this is just in real life. So if you have access to urgently needed material directly on your desktop, you can work quickly and efficiently. However, if you still have to get the missing material in the city and have to take the bus at rush hour, which only runs every hour, your performance will drop. In our portfolio, we can offer a tool named Codee, coming from Pentra Solutions in Spain. Codee uncovers such and other possibilities for performance optimization in the source code and makes recommendations for code changes. In some cases, Codee also carries out these changes independently. So where can it be used? Wherever time-critical algorithms need to be implemented. So, for example, manufacturers of trading systems. So the more transactions they can be processed per day, the greater the turnover. Fraud detection systems that must check a large volume of data overnight. Large data throughputs are also often required in the telco sector. So another area is control engineering. So an aircraft attitude control system does not allow any dead times. And for instance, the electronic stability program and bent engine management programs in vehicles contain time-critical algorithms. In safer technology, so safety valves, brakes, airbags, etc., must be triggered within a specified time frame. So another topic, another task for static analysis is the energy consumption optimization. So optimizing energy consumption is a topic that increasingly coming into focus. This was former only an exclusive domain of hardware. So you may remember the leap from NMOS technology to CMOS technology that saved significant energy. Now, however, more and more attention is being paid to software. There's a particularly high need for savings in the field of supercomputing. So these computers with several million CPUs sometimes have the power consumption of a medium-sized city. And the electricity costs are enormous. So an energy-optimized application can save thousands of euros. In the meantime, the topic has also reached the private sector. You will certainly be familiar with apps on your cell phone that are real power guzzlers and shorten battery life enormously. So I'm not talking about the flashlight function, but apps that really demand a lot of processing power. Energy optimization is particularly important for mobile devices in the medical field. So these include portable insulin pumps or mobile dialysis machines, for example, which require long battery runtimes. Where is the energy actually consumed? So let's take a look at the electronics. Shown here is a simple memory cell made up of 6 transistors. This is a bistable multivibrator, also known as a flip-flop. This is a standard circuit for storing 1 bit. To store a bit in a static RAM or register, you usually need 6 transistors. So how does such a cell work? The transistors are designed to be complementary. You can see that this at the upper ones that have a small circlet here at the gate. They open while the lower ones are closing and vice versa. So in this case, a logical 1 is stored. The transistor I have highlighted in red here is blocked. The one marked in green is open. The upper transistor here is connecting to the operating voltage, which is therefore present also at this point here. And this means that the output Q here is at logic 1. The lower transistor being opened and the upper is closed here in the second part here of this circuit. And that means so that this point here, Q bar, is connected with the ground, and so it's logically 0. And you can switch this over. So if you would like to store a logical 0, so then it flips over here in this state, or this state here, then it stores a logical 1. But please be aware that the advantage of this complementary technology is that one of the transistors is always blocked, and therefore no cross current can flow here or here. This means that practically no energy is consumed. So how does energy consumption occur? So I have energy consumption when the state changes. So in this moment, when the transistors are switching over, then both are open for a brief moment, it's about 1 nanosecond, and the cross current can flow. So energy is consumed at the exact moment when the change of state is happening. So when the bits flip over. So how can you optimize? Quite simply, you have to avoid unnecessary bit changes. So this can be achieved, for example, by avoiding unnecessary memory accesses. So do you remember? I already mentioned this problem in connection with performance optimization. So could it be that performance optimization also means energy consumption optimization? Unfortunately, this is not quite that simple. However, if I carry out a cache-related performance optimization, then I usually also have save energy. If I use the processor's vectorization options, I also save energy. But if I parallelize by creating more threads or more processes, and perhaps by activating additional cores, then I consume more energy. But it is clear that you can use static analysis to find algorithms with the possibility of optimizing energy consumption. Codee identifies these places in the source code and will mark it. So what is the actual order of magnitude of the energy savings of an algorithm? I thought I would measure this, taking the earlier example of matrix access. So I found an old banana pie in the drawer. This is equipped with an Allwinner 820 controller with an ARM Cortex dual-core CPU and a first-level cache of 2 times 64 kilobyte. So why 2 times 64 kilobyte? Because this is a Harvard architecture and program code and data are stored in separate memories. So I ran the matrix algorithm on it before and after optimization and measured the energy consumption for each case. So the operating voltage was a constant 5.18 volt in both cases. And so the additional current consumption of the board when the algorithm is running was 170 milliamperes. This results in a power consumption of 6 watt. As the algorithm was running 16.87 seconds, so the energy consumption was 10.22 joule. After optimization, the energy consumption was only 1.92 joule.